In February of 2023, a paper was submitted to one of the most prestigious scientific journals on Earth. The lead author was an astronomer. The subject was 6 objects detected by a space telescope, and the language used in the paper to describe those objects was something you almost never see in peer-reviewed science. The phrase used was, "too big to exist." Not surprising, not anomalous, too big to exist. The objects in question were galaxies, each one containing hundreds of billions of stars. Each one formed in the first few 100 million years of the universe's history, in the opening moments of cosmic time, when the universe was young and nothing had yet had time to grow large. And each one was, according to the best tested model of cosmology our civilization has ever produced, physically impossible. Not unusual, not at the edge of what the model allowed. Impossible. The amount of matter locked up in the stars inside those galaxies exceeded the total amount of matter that the universe had available to build them at that point in time. The journal published the paper, the scientific community began debating it, and the headlines that covered it for 1 week before moving on completely missed what was actually at stake. This is the story of what the James Webb Space Telescope found when it looked at the early universe, and why what it saw is still shaking the foundations of modern cosmology. This is Deep Space Classified. New classified file every week. Subscribe before we go further. Let's get into it. Christmas morning, 2021. While most of the world was opening gifts, an Ariane 5 rocket lifted off from the coast of French Guiana carrying a piece of engineering that had been 30 years in the making. The James Webb Space Telescope. $10 billion. 100,000 people working on it across 3 decades. A mirror made of 18 hexagonal gold-coated segments, each precisely shaped to collect and focus light from objects so faint and so distant that no telescope ever built had reached them before. It had survived budget cuts that nearly canceled it, a technical disaster that required a complete redesign, a global pandemic that delayed the launch, and a deployment sequence so complex that 344 individual steps, each of which, if it failed, would end the mission permanently, that engineers at NASA referred to it internally as the observatory that had to work perfectly the first time. Every step worked. Webb's mission was to see further back in time than any telescope before it. Light travels at a fixed speed. The further away an object is, the longer its light has been traveling to reach us, which means when we look far enough into deep space, we are looking backward in time. Hubble could see galaxies that existed a few 100 million years after the Big Bang. Webb was designed to see further, potentially to within the first 100 million years of the universe's existence. The goal was simple. Look at the early universe, see the first galaxies, confirm what the best models of cosmology said they should look like. The models were very specific about what those first galaxies should be. Small, dim, primitive, messy clumps of early stars just beginning to coalesce under gravity, having had almost no time to organize themselves into the structured, mature galaxies we see in the modern universe. Webb looked. And the galaxies in the early universe were not small, dim, or primitive. To understand why this matters, you need to understand the model that Webb was supposed to confirm. The standard model of cosmology is called lambda CDM. It describes how the universe formed, how matter assembled itself from the Big Bang into the stars, galaxies, and cosmic structures we see today. It has been developed over half a century. It has survived thousands of tests. It predicts the large-scale distribution of galaxies in the modern universe with extraordinary accuracy, and those predictions have been confirmed by observation again and again. At its core, lambda CDM describes a universe that builds from the bottom up. Small things form first. Simple structures emerge from chaos, then slowly, over hundreds of millions, then billions of years, those structures merge, collide, and grow into larger and more complex ones. The Milky Way, for example, is thought to have been assembled over more than 10 billion years of mergers and accretion, gradually accumulating the mass it has today. Under this model, the very first galaxies, the ones Webb was sent to photograph, should be tiny. They formed in the first few 100 million years of a universe only 13.8 billion years old. They simply had not had enough time to grow large. In the same way that a 1-week-old seedling cannot be a full-grown tree, an early universe galaxy cannot be the size of something that took billions of years to build. That was the prediction. Tested, peer-reviewed, trusted, and then Webb sent back its first data. The galaxies were not tiny. They were not dim, and several of them were not small clumps of primitive stars just beginning to form. They were enormous, bright, fully structured, and some of them had masses that the entire lambda CDM model said were simply not achievable in the time available. The first images Webb sent back in July of 2022 stopped scientists mid-sentence, not because they were beautiful, though they were the most beautiful astronomical images ever captured, but because of what was in them. In a region of sky so small you could cover it with a grain of sand held at arm's length, Webb had captured thousands of galaxies, each one containing hundreds of billions of stars, each one billions of light years away. The image showed more galaxies in that tiny patch of sky than Hubble had captured in weeks of observing its deepest fields. But it was not the number that unsettled astronomers. It was what the galaxies looked like. The ones from the earliest epochs, the ones that had existed when the universe was between 500 and 700 million years old, were not behaving the way the models said they should. They were too luminous, too structured. And when astronomers began calculating their masses, adding up the light from all the stars inside them to estimate how much matter they contained, the numbers that came back were wrong in a way that was hard to explain away. Astronomer Ivo Lebay at Swinburne University led a team that focused on 6 specific galaxies from this era. They published their findings in Nature in February 2023. The conclusion of that paper used language almost never seen in peer-reviewed science. The paper stated appeared too massive to exist, given what we know about the early universe. Not at the extreme edge of what the model allowed. Beyond it, adding up the stars in those 6 galaxies would require more ordinary matter than the universe had available in their region of space at that point in time. Stop and understand what that actually means. The universe began 13.8 billion years ago. In the first few 100,000 years, it was a fog of hot plasma, too dense and hot for atoms to even form. Then it cooled. Matter condensed into neutral hydrogen atoms, and gravity began its slow work, pulling matter together over hundreds of millions of years into the first stars and galaxies. The total amount of ordinary matter available in any given region of space at that early time is not a guess. It is a calculation. It comes from the physics of the Big Bang, from the precise measurements of the cosmic microwave background, the ancient light left over from those first moments, and it is one of the most well-established numbers in all of modern cosmology. The mass locked up in stars inside those 6 galaxies exceeded that number. In some cases, by factors that made astrophysicist Mike Boylan-Colchin at the University of Texas describe the situation as not a tension with existing models, but a crisis. Some of these galaxies appeared up to 100 times more massive than the CDM model said should be possible at that point in cosmic time. 100 times. If forensic evidence at a crime scene contradicted your model of what happened by a factor of 100, you would not adjust the model around the edges. You would reconsider the model from the beginning. That is where cosmology found itself in 2023, not at an edge case, at a fundamental question. What is happening in the early universe that our best model, tested and trusted for 50 years, completely failed to predict? Then, in May 2024, Webb added one more data point that sharpened the problem. A team analyzing Webb's deep field images confirmed the most distant galaxy ever observed by any telescope. They named it JWST 14-0. It existed 290 million years after the Big Bang. The universe was not yet 300 million years old, and this galaxy was already there, already large, already luminous, already producing light. But the detail that stopped scientists was not its distance, it was what the galaxy was made of. The spectrum of light coming from JADE's GS-14-0 showed the chemical signature of oxygen. Oxygen is not a primordial element. It cannot have existed at the time of the Big Bang. Oxygen is produced inside stars, forged in stellar cores over millions of years, and then scattered into space when those stars explode. To have oxygen in a galaxy that existed 290 million years after the Big Bang means that previous generations of stars had already formed inside it, lived their full lives, and died. All in less than 300 million years. stars that our models say had not yet had time to exist, in a galaxy our models say was too young to have had multiple stellar generations, producing an element that requires stellar generations to create. It is not impossible in every theoretical framework, but it is, in the framework that has governed cosmology for half a century, deeply, profoundly wrong. So what are the explanations? What do scientists actually think is going on? There are three serious possibilities, and none of them is comfortable. The first is that the galaxies are not as massive as they appear. Specifically, some of these early galaxies may contain not just stars, but extremely active supermassive black holes at their centers. These black holes, called quasars, can shine with the luminosity of 1 trillion suns, making their host galaxy appear far more massive than it actually is, because astronomers may be mistaking quasar light for starlight. If Webb is miscalculating mass because of contamination from active black holes, the galaxies may be more normal than they look. Researchers have checked for this, and yes, some of the early galaxies do show signs of active black holes contributing to their luminosity. But even after accounting for that contribution, a substantial number of galaxies remain too massive. The quasar explanation reduces the problem. It does not solve it. The second possibility is that star formation in the early universe was dramatically more efficient than the models assume. Under lambda CDM, the process of turning gas into stars is self-limiting. Stars produce radiation that heats surrounding gas and slows further star formation. But some researchers now believe the early universe's conditions, denser, hotter, with different physical dynamics, may have allowed periods of explosive star formation that the models never accounted for. Short, intense bursts that built massive galaxies in a fraction of the time the standard model requires. This explanation does not require throwing out lambda CDM, it requires modifying it, which is scientifically less alarming, but it means the model was meaningfully incomplete. The third possibility is the most unsettling, and it is the one that some very serious physicists have begun taking seriously in peer-reviewed papers. What if the universe is older than we think? The universe's age, 13.8 billion years, comes from a single measurement, the Hubble constant, a number describing how fast the universe is expanding. Measure the expansion rate, run it backward in time, and you arrive at the starting point, the Big Bang. For years, there has been a problem with that measurement. Two completely independent methods of measuring the Hubble constant give two different answers. The first method uses the cosmic microwave background, the ancient light from the Big Bang, and gives a value of approximately 67 kilometers per second per megaparsec. The second method uses measurements of nearby supernovae and variable stars, the so-called cosmic distance ladder, and consistently gives a value of approximately 73. The gap between those two numbers is small, but it has persisted through decades of increasingly precise measurements from both methods. It has not gone away when better instruments were used. It has not narrowed as data improved. It sits there and unresolved, and astronomers have a name for it: the Hubble tension. If the true expansion rate is different from what either measurement gives, the age of the universe is different from what we currently calculate. A higher expansion rate means a younger universe. A lower rate means an older one. And an older universe, even 1 billion or 2 billion years older, gives the early galaxies more time to assemble their mass, more time to produce the oxygen. In 2023, physicist Rajendra Gupta at the University of Ottawa published a peer-reviewed paper proposing that the universe may be as much as 26.7 billion years old, nearly twice our current estimate. Most cosmologists consider that extreme. But it was peer-reviewed, it was published in a legitimate journal, and the conversation is happening. The Hubble tension is real. The impossible galaxies are real. Whether they are connected, whether the resolution of one explains the other, is a question that modern cosmology is actively trying to answer, and has not yet answered. Here is what makes this different from every other scientific anomaly you have heard about. This was not found by accident. Webb was built specifically to look at this region of cosmic time. The impossible galaxies are not a measurement error or an instrument glitch. They have been confirmed by independent research teams using independent methods. The spectroscopic distances, the measurements that confirm these galaxies, are genuinely from the early universe and not nearby objects mislabeled, were confirmed by astronomer Emma Curtis Lake and her team at the University of Hertfordshire using Webb's spectroscopy mode. The distances are real, the galaxies are at the distances claimed, and Webb keeps looking. Every additional deep field image, every additional epoch of the early universe observed at high resolution adds more data to a dataset that is already challenging a fundamental model of how the cosmos assembled itself. The data is not going away. The tension is not softening. And the three possible explanations, systematic black hole contamination, dramatically faster early star formation, or a universe older than we think, all carry enormous consequences for what we thought we knew. If it is the first explanation, our models of how galaxies form need revision. If it is the second, the early universe was a dramatically more violent and productive place than we imagined. If it is the third, every distance in the universe, every calculation of how large the observable cosmos is, where everything is, and how it got there, needs to be recalculated from scratch. And here is the scale of what James Webb is still doing right now in 2026. The telescope is in a stable orbit at a point in space called L2, 1.5 million kilometers from Earth, always keeping Earth and the Sun behind it so its instruments stay cold enough to detect infrared light from the most distant objects in existence. It has enough fuel to remain operational for at least 20 years, possibly longer. Every week, it is imaging new fields. Every week, its data is being downloaded, processed, and analyzed by hundreds of research teams around the world. Every week, new papers are being published revising what we know about galaxy formation, star formation rates, black hole growth, and the chemical history of the early universe. The Impossible Galaxies paper was from 2023. It was not the last one. It was not even close to the last one. Webb is adding data faster than cosmologists can fully absorb it. The model that governed the field for 50 years is being tested against higher quality observations than it was ever designed to face. And the tension between what the model predicted and what Webb is showing is not going away. The telescope cost $10 billion. It took 30 years to build. And one of its first significant findings was proof that something in our most trusted model of how the universe works was wrong in ways we had never anticipated. That is not a failure. That is science doing exactly what science is supposed to do. Webb's first deep field image showed a patch of sky the size of a grain of sand held at arm's length. Inside that patch, thousands of galaxies, each one containing hundreds of billions of stars, each one billions of light years from the next. And scattered among them, in the earliest epochs that light can reach, galaxies that should not be there, galaxies that arrived at their size too fast, galaxies containing elements that required dead stars to produce, galaxies that the model said were impossible. They are there anyway. The question cosmology is now working to answer is not whether the galaxies are real. They are real. The question is what they tell us about a universe that is clearly more complex, more dynamic, and more surprising in its earliest chapters than half a century of theory prepared us for. What do you think the explanation is? A model that needs adjustment, or something more fundamental that we've been getting wrong? Leave your answer in the comments. This is exactly the kind of question where I want to know what you think. And if you want to be here when Webb drops its next finding that nobody expected, subscribe and turn on notifications, because based on the last 4 years of data, that is a matter of when, not if.